Today we are going to talk about system design of a search bar in a website like Substack, where you have to search for different articles. Now, why is this system design video even important? Why is search bar functionality? Search bar is not just over the UI which you are seeing just on the basis of text. We are making a full search from the database of what articles to bring, and you cannot directly query your main database for search functionality because first of all, your main database should be used to actually serve the content and not for search purposes. Second thing, if you keep making search queries to your database, which is your main one, that can crash. So generally it is a good practice to separate the search from the main database. So how do we build a search system, even that simple search bar in a website like you see on Substack? So first, let's talk about the functional requirements. So we should be able to search across all the articles. We should be able to find related articles. We should have the ability to sort search results by created date or popularity. Also, we should be able to handle typos in search. For example, if someone search JavaScript, we should be able to provide them the suggestions for the articles like JavaScript. It should not be always like the search, the text which the person has written and just bring that. We should be able to provide these suggestions. So these are the functional requirements which we are tracking. There could be even more functional requirements if you want to support search in different languages. So that could be one requirement here which we are not covering for now. Then comes the non-functional requirements. So we are targeting latency should be less than 100 milliseconds for the search results to appear. Second, your service should be highly available, like 99.99%. Now, why this 1 9 or 2 9s even differ? This is called 4 9s availability. If you reduce 1 9 out of this, let's say if it is 99.9%, then a system becomes much easier to build because it can fail more. And even if you add a single 9, like if you make it 99.999%, it will make your system even more complex. Your system has to be available and has to be resilient 99.999% of times. How much does adding a 9 makes a difference? You can read about it that you start from 5 days and then you come to like maybe 1 hour of downtime in the whole year, not a day, whole year. Next, we talk about the APIs which will be in this search system. So in the search bar, we should be able to give suggestions. So there would be one API with search suggestions. This will be a simple lightweight API. This will just give the suggested text entries. For example, when someone starts typing IPH, it should give suggestions like iPhone 15, iPhone case, iPhone charger. So when are these API calls made? Do you make these calls on each type, like when you type I, P and H in every call, do you make this? So if you do this, your system would crash. So generally a technique is used to prevent such high load of the API calls so that not on every character the call goes. That technique is called debouncing. So what this technique does is that it makes a call on every fixed timer. So generally the timer taken is 500 milliseconds. So if after the last keystroke the person has made, after that if 500 milliseconds have passed, then this API call is made. This debouncing technique is done on the front end itself. The second API which we need is the search, which will do the full search results, which will give a list of all the articles which we are searching in our search query. So it will have a query which will be the search query. We will have page because this would be a paginated API. For example, if there are hundreds of results, you display first 20, then add the page number, fetch from 21st, and that's why you need page number. Size is again that is dependent on your pagination of the page which you bring. Sort by relevance or popularity or created time. So on the basis of these, you should be able to provide sorting, and your response would simply look like a JSON which will have the results. Now, how will the design look like? Whoever are doing the search on the search bar, they will make a call. Between users and the application servers, there will be a load balancer which will balance this load amongst the application servers. The application servers will then fetch this data from an ElasticSearch cluster. Now, why are we using ElasticSearch? We'll talk more in detail about why this choice. So what are the benefits of this using Elasticsearch for providing this search? Elasticsearch provides us a reverse index over the keywords. For example, let's say there is a complete article on, let's say, Rust. So what it will do, like all the articles, whatever content is there. So for that content, there will be a reverse index created to the document ID. So in the content, if there is Rust being mentioned, a reverse index to that document will be created using this. So that is what we need, because we don't need to just fetch results on the basis of article title. Also, it should be able to give the results on the basis of article's content. That's why we need a reverse index over the keywords. It also provides various other benefits, and the major benefit it provides is that almost all the fields in the document what you have, it provides a reverse index over that, so you don't have to do anything extra for it. The second thing is it also allows partial text search. For example, if, like I mentioned, if someone searches for, let's say, Java, it should be able to fetch the results, all the related results for JavaScript also, Java also. Now, how to put this data into the Elasticsearch? Like I mentioned at the start, we should have a main database and we should have a separate search database. So let's say we have this as our main database. The user makes a query to this main database. The user writes an article and that article is stored in this main database. Now, how will this article be indexed in our Elasticsearch cluster? Or not even just writing, maybe just updates the main database, updates that particular article. So how will we update the Elasticsearch cluster with this new article or this updated article? So to make these updates, there are multiple options that the user makes API call to both update the main database and update to Elasticsearch. This will result in high latency because you want the data to be present in both the locations, so you cannot return success even if it is successful in one database and not in the Elasticsearch, or vice versa. That's why you cannot go with this approach. Also, it can lead to various problems because it is not possible to do both these things in a single transaction. It is possible that one is in an inconsistent state than the other. Second thing is update later, that you update in this main database and update the Elasticsearch cluster later with some latency and provide eventual consistency. So this is the model which is generally used, and this is fine for our use case. But it also has caveats, like how will we update later? So should we scan the whole database after every fixed intervals? This will cause a huge load over your database. So this approach is never the right approach. You cannot scan the complete database after each updates. Maybe just one article was updated and you read the whole database for it. Maybe you just scan the new articles, what new articles come. But in that case, you will lose out on the updates. It is possible that there was an article which was updated and you don't bring it. Now, the third thing which comes up is what we will use and what is the industry practice to use: change data capture. Now, what is change data capture? Change data capture is nothing but whenever an update comes to this main DB, it will result in a message that this part of this document has changed. And this message we will process and finally make the update in the Elasticsearch cluster. So let's discuss what will be the architecture of this. So whenever user makes an update to the main database, there will be an event which will be put into a distributed queue. We can use AWS SQS for this. And we will have this workers to process these messages, which will take this message and update the data in our Elasticsearch cluster. Now, suppose a message fails in processing, we can have a dead letter queue, which we also call a DL queue. So if a message fails, we can just retry those failed messages from this dead letter queue. Now, it is possible that a new update has come and that has taken already effect. And now when we process this old message, then we don't need to update it because the new message has already changed what was there. So our worker has to be intelligent, it has to be idempotent, it has to make sure that this update is the newest update. If it was an older update and a new update to the field has already taken place, then we'll just ignore this message. Now, what other benefits this approach provides is that you don't have to make updates with each event. You can do a batched update. So you can take a list of events and update that in a batch in your Elasticsearch cluster. This reduces the number of calls you make to this Elasticsearch cluster, also eventually reducing your cost also. Why not Kafka? You can ask, like, why did we use a queue like SQS and not Kafka? It is simply because we do not expect such a high throughput to come here, and Kafka is mostly suited for even higher throughput events. For example, a leaderboard system where the scores are changing every second. Here a person is just adding an article and we don't expect the load to be that much that we need Kafka for this. Another thing which you might ask, why not make a direct API call? Why do we even need to have this in between? Whenever a new event comes, why not make a Elasticsearch cluster update call? It will hammer the Elasticsearch on each update. So like we discussed, we are doing batched updates. If we keep on hammering ES on each update, the number of calls which come to Elasticsearch would be large. So the queue acts as a buffer and the worker batches your events and then makes the call to the Elasticsearch. So what should be the contents of this event which is being generated by the database? Should it just have the updated fields of a document? For example, a new document comes, then a complete document. But if let's say just one field, maybe less title is updated or the content is updated, so just those fields should be sent in this event. Or the complete document. For example, if an article is updated, then we send a complete document in this event, or we just send the ID of the document and then Elasticsearch cluster, and then the worker for this event will fetch the data from the database and then update in the Elasticsearch. Now all these three approaches are used by some people. Each of these has different pros and cons. We'll discuss these. So let's say you just go with the updated fields. So in this, your worker should know the state. It should know that this update is in order. You cannot process events out of order. All your events should be in order. Now how do you maintain order? You can either use a first in first out queue, FIFO queue. That is also a possibility in SQS, but the problem with FIFO queue is that their performance is very bad and they are generally not preferred. So what other way you can use? You can use some kind of field. You can use some kind of marker in this updated event that this, and keep that sequence maintained across each document, which is also a big pain. So generally this field is not preferred. It can be built, but it is efficient also, because on the network you are just sending the updated fields, but it is quite complex to build. Then comes the next thing, which is full doc. This is very easy. Any update, just send the full doc. It will take more network, more bytes egress, but this can be made idempotent easily, because you know the version of your document. You know that this version is new or it is old. You simply just update whatever document comes and update in the Elasticsearch. And if it was an old version and a new version already exists, then just discard this. So this is very easy to use and you can always start with this. But like I said, this causes a lot of network usage and egress costs. Then comes fetch from DB. So this will cause hammering your DB, because what will happen is that you send an ID in the event. The worker will take this ID and then make a call to the database, read from his read replica, and then update this in Elasticsearch. This is actually the most idempotent approach, because every time a message is processed, you will make sure that the data is always correct. So maintaining correctness is this is the best approach, because you don't have to take care of anything, because your DB will have the required things, but it will hammer your database. So it is good for very small scale, but not for a large scale. So generally the most go-to approach is going with the full document approach. So now this is how your complete system is built. How the data goes, how is the data fetched, we discuss both. Now if you want to learn more about Elasticsearch, that I'll cover in detail in some other video, but for now I'll just give you a glimpse of it. So what is Elasticsearch that we are using here? Elasticsearch internally maintains a Lucene index. What is a Lucene index? It is just an inverted index. What data structure it uses, that can be another video in itself. So it uses Lucene index to make an inverted index from your content to the document ID. Now in Elasticsearch cluster, there are multiple types of node. One is master eligible. That means these nodes can become master. Then is a dedicated master. This is the main master node. Now this master node, what does it do? These master nodes, whenever they are connected, they just make sure that the coordination is working fine, the cluster is working fine, and they do not store any data. For data storing, there is a separate node called the data node, which actually stores the data, handles search, indexing, what we talked about. And there is an ingest node, which pre-processes these docs and then ingests into the Elasticsearch properly. So it is possible that some mapping may be required from what the data structure, from the whatever data format is from your main database and the Elasticsearch. So this pre-processing, whatever happens, this happens in this ingest. Then this is coordinating only node. This coordinating node coordinates, like whenever a request comes, first it will go to ingest node, then it will go to the data node, and then it finally returns. So this is the node which just coordinates. Then there are some other nodes also, like ML node, which is not always used. You might not never need it if you're not running any analytics. Then there is a transform node, where there is data transformations are required. It is possible that you want to do some aggregations also, for example sum over some fields. So these kind of aggregations and transformations are done on the transformation node.